When I was putting this presentation together, I was just having a little look around, and I come across this on Twitter from Brian Cox, and it was just a little message from Brian Cox in regards to the conference, and he says perhaps they could put this quote below: "Everyone attending this conference is a shitbox." So that's what Brian Cox thinks of flat Earth conferences. It was just a little bit of fun, like to try and break the ice.
There is absolutely no basis at all for thinking the world is flat. Nobody in human history, as far as I know, has thought the world was flat.
The problem is, every single ancient civilization in history believed or knew the earth was flat. Yeah, where you can look at the Norse, the Hebrews, the Mayans, the Incas, the Navajo, you name it, every single ancient cosmology depicts a flat earth. Yeah, I mean, does the Egyptian cosmology look like a spinning ball in outer space? I don't think so. You know what I mean? You've got the flat earth at the bottom, you've got the firmament above it with the stars, and there you've got Nut, who actually swallows the sun and spits it out the other end, and the moon. So as you can see, all ancient civilizations depicted a flat earth. And one of the questions what gets asked whenever you see somebody on TV and they go, "Hey, Bill Nye, is the Earth flat or round?" And they say something, and he goes, "It's round." And he says, "Back in ancient Greece, in Alexandria, when the sun was in a certain position and the light shone down a well, hundreds of miles away at Siam, there was a stick in the mud, and it actually measured the Earth." And that's how we measured the Earth, which is absolutely a load of nonsense. You know what I mean? Yeah. What did they use to pass the information from one point to the next? Carrier pigeons. You know what I mean? It's 2018, and when you ask a reputable scientist, yeah, proof of Earth's curvature or proof that we live on a globe, they refer back to ancient Greece. You know what I mean? It's 2018 now. For me, landing on the moon in 1969. What we should have in this day and age now is a 4K camera on the moon, fixed, looking at the Earth, rotating orbit. Yeah, but we don't have none of that. You know what I mean? It's nonsense. And I don't know if you've. I've said this quote a few times. This is a famous quote from Nikola Tesla, where he says, "Today's scientists have substituted mathematics for experiments, and they wander off through equation after equation until they build a structure which has no relation to reality." What he's saying there is basically everything we get from scientists today is theory. There is no observations.
Kepler's first law states simply that Mars travels in an elliptical orbit, with the Sun at one focus of the ellipse. Although he chose to list it first, Kepler only came to this conclusion after figuring out his second law, which says that if you draw a line from the Sun to Mars and wait a fixed amount of time, that line will sweep out a certain area as Mars moves along its orbit. What Kepler noticed was that this area is exactly the same no matter where in the orbit you are. This is often phrased as Kepler's equal area and equal time law, and this law works because Mars doesn't move at a constant velocity. It speeds up the closer it gets to the Sun. So if Mars is approaching perihelion, the point in the orbit nearest to the Sun, it's traveling faster than if it's at aphelion, the point that's farthest away. In the first case, the line connecting Mars to the Sun is very short, but because the planet is moving faster, it covers a lot of distance. In the second case, the line segment is much longer, but Mars also moves more slowly. Either way, the area swept out in a fixed amount of time is the same. Kepler and his contemporaries could see that Mars doesn't move at a constant rate, but they didn't know why. This inverse relationship that Kepler proposed between distance from the Sun and orbital velocity could explain the puzzling observations of Mars movements, but only if the orbit is an ellipse. A circular orbit would mean no change in distance from the Sun with time, and thus the velocity would be constant as well. These two statements, that Mars travels in an elliptical orbit and that its speed varies so that the Mars sunline sweeps out equal areas in equal time, were generalized to include all planets in 1621, and they constitute Kepler's first and second laws of planetary motion.
Interestingly, when they showed that video, they actually debunked themselves by showing you that video, because the first thing what you'll notice on an elliptical orbit, you need two focus points or two foci for an ellipse to work. But you see, they've got the sun in one focus of the ellipse, but there isn't a second focus point. Now, that should destroy the ellipse without that second focus point, because one single point will make a concentric circle, whereas they're telling us that the elliptical orbit's like slightly off center shape. Yeah, but you need a second focus point for that. And interestingly, after Kepler's law of planetary motion, William Herschel actually set the sun into motion, because the sun was actually stationary up until that point, but he actually put the sun and all the rest of the solar system into motion, which then again absolutely destroyed the ellipse, because instead of getting elliptical orbits, then you got cycloidal orbits, or like spirals or springs. So he basically destroyed the actual ellipse. And not only that, Kepler's law of planetary motion was built up on the back of observations which were recorded by his predecessor, Tycho Brahe. Now, Tycho Brahe made his observations of Mars in the late 1500s. This was before the telescope was actually invented. So all Kepler's laws are built up on observations before the telescope was even invented. I know that they had some clever little gadgets back then, astrolabes and what have you, but compare Tycho Brahe's observations to my observations. I'm using the latest optics camera equipment, and I'm using GPS coordination to make my observations. So yeah, people mock me when they say, "Oh, you're debunking Kepler's law with a camera and a phone app." But there is only like flat earthers making observations, and one of the main tools for the flat earther is this beast, the Nikon Coolpix P1000, aka the Curve Buster, I call it. My friend Jennifer lives in Buffalo, New York, and on a regular basis she goes to Lake Ontario and she shoots the Toronto skyline from 30 miles away. So I'm just going to play a little video clip now. There's no sound to this video, but what you'll see here, yeah, she's used the Mick West Metabunk calculator, which measures the alleged Earth curvature. Now, at a distance of 30 miles, you're looking at 516 feet of hidden curvature. That's based on a ball 24,901 miles in circumference. Now, also, what you have to take into consideration, what Mick West did, you see, because flat earthers were beating the old Earth calculator, he created this new Earth calculator, which actually calculates the standard refraction into it. Yeah, so it makes it harder, yeah, to disprove the globe model with his calculator. But Jennifer's observation actually beats Mick West's Metabunk calculator. So I'll just play it here, and as you can see, she's at the seashore. So this is 30 miles away from the Toronto skyline. What you'll see in the right-hand corner now are overlays. All I'm doing there is just showing that the temperatures are all within 4 degrees of each other from both locations. You see that little white building there, the Rogers Centre?
Mm-hmm.
That little white building there?
Yeah.
That should not be visible whatsoever. Yeah, but as you can see, on a clear day, you can't see it every day due to weather conditions. You know what I mean? There's ever changing atmospheric conditions. But on a clear day, what you can see is that Rogers building. And just here, I'll just read this out. So the Toronto skyline at 30.84 miles away from Fort Niagara, New York, the Rogers Centre Dome is only 282 feet high. Lake Ontario is 243 feet. The base elevation of the Rogers Centre is 267 feet, making the total height of the Rogers Centre 306 feet above the lake. Jenner's elevation was approximately 6 feet, and that is being conservative because I'm sure Jenner's not six, her eyeballs don't stand at 6 feet tall, so you're probably talking 5'4" where the eyeballs sit, you know what I mean, or the actual observation point. So she's being quite conservative with 6 feet. So she's 6 feet above the lake. Alleged curvature should have been 516.85 feet of drop, according to that Nick West calculator. The Rogers Centre should not have been visible. And just like I said with them overlays, the temperature of Toronto, Fort Niagara, and Lake Ontario were all within 5 degrees of each other, and the humidity was quite, well, it's really low, you know what I mean? It's at 43%. Now, if you went there on another day and the humidity was 65%, are you going to see the Rogers Centre? No, you're not. You probably won't even see the Toronto skyline on certain days. Yeah. So the question is, like, there's only one reason why we would be able to see that from that distance, and that's if there's no measurable curvature. But what mainstream will tell you, I'm sure you've seen the Joshua Nowicki image of the Toronto skyline from, I think it was 46 miles away. And when Fox News got hold of that, they says, what you're seeing here is a superior mirage. Yeah. Now, I beg to differ, because if you look at this image here, what you'll see is, you see that bottle, you can see the red juice in it. Now, you can see the actual juice there. What you'll see is the light refraction actually bends the image down. So what you're actually seeing is an inferior mirage. Yeah, they're telling us that that object is magically rising up from behind the curvature. I'm saying the refraction is mirroring that image down. Like I say, if you look at this image, this is shot on a flat surface from a distance, and when you zoom in, what you do, you get that light refraction bending the image down, and you'll notice the reflection bending down. You see, you can actually see it mirrored downwards. Yeah. So what we're saying is that when we're observing skylines or whatever lighthouses from a distance, yeah, we are seeing the light being bent down and not magically rising up from behind the curve. So I think that's a good observation, and I think Jenna did a cracking job by showing that the image is actually being mirrored downwards and not rising up. Does that make sense?
Yeah. Yeah.
And here's a good example of that. Lake Pontchartrain, where you see the I don't know if some kind of telephone towers, but if you look at it, what it does, it looks like it's curving over the actual ocean. Now, what I've just showed there above is that mirror effect where the actual image is being mirrored downwards. I mean, if that was reality, yeah, we'd have to live on a kitchen roll holder. So, but moving on, one thing that's always apparent is the horizon, which is always at your eye level. Yeah. So whether you're at Lake Pontchartrain looking out across there, or whether you're on the beach, there's my foot there where I'm lying on the beach in Fuerteventura. Yeah. Horizon is at eye level. You go to Mount Everest, the horizon is still at your eye level, or you go up to 120,000 feet. And again, the horizon or the horizontal eye zone is still at eye level. Now, on a ball, yeah, that shouldn't happen because it should actually roll away from you. But what you'll see is the horizon is always at eye level. And what I did, I actually went a step further than that. And I looked into the GoPro Awards where the SL-10 amateur rocket was sent up to, I do believe, 396,000 feet. Yeah. Now, that is like a world record for an amateur rocket. And what you'll see, even though it used a GoPro lens, yeah, when you get that horizon equidistance, you'll see it's perfectly straight. Only when the camera is bent downwards that you will get like a convex horizon, and when the camera is faced the opposite direction, you'll get a concave horizon. But like I say, when it's equidistance, it's a perfectly straight line. What you have to take into consideration for as well is that image is shot with a 180 degrees cam. That camera can see 180 degrees. So there's a lot of horizon there. You know what I mean? And all I did there was I took that line tool there up there, and I just put it from that point to that point, and it makes a perfect straight line. The only time we see curvature is when we see things like the Red Bull space jump with Felix Baumgartner. Yeah, as you can see there in the background, you've got a nice big curved earth on the top. Remember, it says when the camera is face down, you get that convex image. Notice the horizon line is not at eye level now; it's gone past your eye level. Only when it's at eye level and equidistant do you get your perfectly straight line on the horizon.
And not only that, they made sure to photograph him standing there with a really wide-angle lens, which curves horizontal lines. Right. So in the photo, you see this curvature of Earth's surface, and you say, wow, he's in space, look at that. No, he's not. At that height, you don't see the curvature of the Earth if you are 2 millimeters above this beach ball. You just don't. That stuff is flat.
And that's from Neil deGrasse Tyson's own mouth. So whenever you're up against a globularis and they say, I've seen the curvature of the Earth from an airplane window. No, you haven't. You know what I mean? If you go up to nearly 400,000 feet, you still can't see no Earth curvature. So where does Earth start curving? You know what I mean? 400,000 feet is 70 miles up. Yeah, it's a long way up. Neil claims that the Earth is a sphere, but it's not a perfect sphere. It's slightly oblate. It's an oblate spheroid. Not only is it oblate, but it's slightly chubbier below the equator. Basically, it's pear-shaped. Now, what I'm going to do, I'm going to just read you a quote out from Zetetic Astronomy from 1904, and it's on page 14. This is straight out of the book. It says, theory, first of all, makes the Earth to be a globe, then not a perfect globe, but an oblate spheroid, flattened at the poles, then more oblate until it was in danger of becoming so flattened that it would be like a cheese, and passing over minor variations of form, we are finally told that the Earth is pear-shaped, and the ellipsoid has been replaced by an apoid. What shape it may assume next, we cannot tell. It will depend upon the whim or fancy of some astute and speculating scientist. I think that's brilliant. So, my observations. What I did here, I used an app called Alptra, and I just set my compass at 0, well, nearly 0, and I just took a photograph with the app. It takes a little snapshot and it gives you an azimuth reading and a declination angle. What you can see from that reading there is that the app I'm using, it's pretty accurate. There you can see, look, I've placed it at north and I've placed the app over it and took a little snapshot to show that the readings I am taking match up with the compass. All my observations were made using the Nikon Coolpix B700. I always recorded at the same frame rate, which was 60 frames a second, the same zoom, which was about times 50, and from the same location, which was from my back garden in Ripley at the time. So I've always recorded my readings from the same spot. And not only that as well, I always try to catch the moon at my zenith, which was 180 degrees from my location at the time. Now I just want to give you a little bit of a comparison between flat Earth and globe Earth observations. On a flat Earth, one of the first things you'll learn about is perspective. And we learned that when a celestial object is closer to the observer, it will appear higher in the sky. And when a celestial object appears further away, closer to the horizon, that's how we judge it. That's how I judge it anyway. And I'm sure there's a lot of people out there who think the same. But interestingly, from a globe Earth perspective of the moon, when the moon's high on the Tropic of Cancer, it's not because it's closer to the Earth. It could actually be at apogee at that point in its cycle. It's because of that 5-degree inclination. That's what puts the moon high in the sky in their model. But from a flat Earth perspective, I judge it when the moon's high in the sky. I judge that moon being close to me, and when it's further away on the horizon, it's lower down. When I was in the hotel at the convention, I come out to the corridor and I thought, wow, that's a long corridor. So I took a photograph of it. And what you'll see is these lights, they're all the same size, but it just looks like they're getting smaller and smaller and getting closer to the horizon, just like celestial objects do. The only difference with celestial objects, like the moon, is it doesn't get smaller as it goes further away. There is a reason for that, and it's called atmospheric lensing. That's why the moon, it actually gets bigger as it gets close to the horizon, because you're looking at the moon through more layers of atmosphere. It will appear bigger on the horizon than it does when it's up high in the sky, because you're looking at it through less layers of atmosphere, if that makes any sense. My first observation when the moon was on the Tropic of Cancer, and what you'll see here, the moon is in what I call the northern circuit, and it basically follows the actual stars. It does that all the time, and I took a snapshot on the 6th of March 2017. There you'll see the moon phase, which is a waxing gibbous moon. I also took a snapshot from NASA's Lunar Reconnaissance Orbital platform. Basically, this tells you the position of the moon from a globe Earth perspective. It tells you how close the moon is to the Earth. Obviously, when it's at 28 there, that's 28 Earths away. And when it's at its furthest point, that's 32. So the 28 would be perigee, and the 32 would be apogee. One thing what's quite difficult to get your head around, from a globe Earth perspective, when the moon would actually appear to speed up in the sky, it would be when it's at actual apogee. I know this is difficult to get your head around, but when it's at its slowest point in the cycle, that's when it would appear to speed up on a spinning globe. So just keep that in mind, because that does become quite important later on. Keep that in mind. But on the night of the 6th of March, I took a diopter reading, and as you can see, at that point, the moon was at 187 degrees, which is just roundabout south, where I always like to catch the moon at zenith, and it was high in the sky at 56.1 degrees. That's the declination angle. So it is quite high in the sky, as you can see there. I also compared my readings with MoonCalc. You know what I mean? It'd be a bit daft if I pointed my app at the moon. It said it was at 180 degrees, and I went onto MoonCalc and it said it should have been at 270. There'd be questions being asked. So as you can see, their readings on the time of my observation was 183 and 55 degrees. If I just click back, you'll see mine are 187, 4 degrees out, yeah, and a little bit out on the declination angle. One thing you have to keep in mind, yeah, I'm using a phone app which uses GPS, and you have to calibrate it. So you basically have to swing your arms around like a madman in your garden and do somersaults and all sorts to try and calibrate the actual app. And even if you move like a millimeter, it can be the difference of like 4 or 5 degrees. It's so difficult to get it absolutely spot on. So then, 1 week later, when the moon crosses the equator, as you can see, it travels in a fairly straight line when it's on the equator. Interestingly, the moon crosses the equator 26 times a year compared to the sun, which only crosses it twice. Not a lot of people know that. Well, they probably do now, like, but I didn't know that when I first started researching flat Earth. I thought the moon followed a similar path to the sun, but it clearly doesn't. So then again, on the 13th, a week later from my first observation, on the 13th of March 2017, the moon was nearly at full. So I took a little shot of the moon there. And also I took a snapshot from NASA's Lunar Reconnaissance moon phases. Interestingly, the moon's in the night sky there, and on a rare occasion, you can see a full moon in the daytime. That should be impossible in the heliocentric model. Just like an eclipse, when the when the actual moon rises in the daytime, already eclipsed. It's impossible. It should be impossible, but it happens. So then again, I took another reading on dioptra, 182 degrees facing south again, and you'll notice the declination angle now has dropped down to 39 degrees because the moon's heading south, so it will appear lower on the horizon. A confirmation with MoonCalc. Moon azimuth on their website was 178 degrees and the declination angle was 39. So again, 4 degrees out, which is acceptable in my mind. So I'll take that as being pretty accurate. So my third observation, when the moon, a week later, when the moon's on the Tropic of Capricorn, as you can see now, it's actually below that celestial equator, and it's in what I call the southern circuit. I'll just play that again so you can see it again. I'd just like to thank Jenna Fredo for the first time lapse from the Tropic of Cancer, and my good friend Jose Manuel Silva for this one he captured last year. I'll pick up on that later on anyway. Interestingly, this is where the moon should start speeding up in its cycle, but it shouldn't be like just a sharp increase in speed. It should be a varied increase in speed from one point to the next. So it should spend the first half of its cycle speeding up to apogee, and as it passes that point of apogee, it should spend its next point of the cycle slowing down. Even though that's the point where it actually speeds up on the globe, it will appear to slow down from a globe Earth perspective, like I mentioned before. There you see again, I took a reading. What you'll notice this time is I didn't quite catch the moon at south. There's a reason behind that. I've got a full-time job and I start work at 5:30 in the morning. As you'll see there, I left it as long as I could before I shot the moon. It was 5:16 and I then have to pedal 4 miles on my bike to start work at 5:30. So I was trying to rush the moon along to get in position, but I just had to take it as it was for that night, which I don't think it makes a lot of difference. So, but that's the reason why I didn't catch it at south. But you can see I took a MoonCalc reading to match up there at 5:16. The reading is 159 azimuth and 15.1 declination angle. 158 azimuth on mine, 15.1. What I did then, I basically raced the moons against each other. So I also color coded them. So the moon, when it was on the equator, I've color coded yellow. The Tropic of Cancer, I've color coded red, and the Tropic of Capricorn, I've actually colored blue. I did actually get the idea from Stan to color code them because it's a good idea because you can always refer back to it with the colors as well, which also makes it a good reference point. So thanks to Stan for that. I did my first observation, yeah, and then on my second observation, the moon speeded up. So at the time, I was following the circle AE map model, so I expected the moon to speed up on the Tropic of Capricorn. But what you'll see in a minute is quite interesting. the fastest one was the moon on the equator, then the Tropic of Cancer, and then the Tropic of Capricorn. In reality, the moon on the Tropic of Capricorn was just a tad faster than the moon on the Tropic of Cancer. Might sound a little bit confusing, but the reason behind that is, for some reason, even though I shot the moon from the same zoom, the moon appeared smaller that night in that position, and that's why the moon looks slightly smaller. But it was definitely shot from the same zoom, from the same location, which I've showed you from the diopter readings. It was all at the same position, but it did appear slightly smaller, which I did notice. So what I did, like I always do with all my observations, I always make my observations when the moon is at my zenith. Now, zenith is when the moon is at its closest point. So between rising and setting, it's that point smack bang in the middle. Now, my zenith and everybody's zenith in the northern hemisphere will always be 180 degrees south for every observer. So everybody in the northern hemisphere, their zenith point will be 180 degrees, and everybody in the southern hemisphere, theirs will be 0 facing north. Yeah. So what I did on the night of the 23rd of August, I took a diopter reading. Yeah, as you can see, I always catch the moon at 180 degrees. That's to try and keep my observations consistent. Because, like I say, if you're going to measure the moon, if you measured it when it's rising, then apogee, then you measured it when it was at zenith, when it was at perigee, you're not going to get a consistency. So if I do it at 180 degrees south, which is my zenith, the moon's closest spot, I'm going to get a more accurate reading. So as you can see there, on that night, the moon was at south. It was 182 degrees, and it was quite low on the horizon. It was only I think it's about 9 degrees. There was a little bit of a discrepancy between my reading and Mooncalc's reading, which I'll show you in a minute, but I think there's about 3 degrees in it. So as you can see there, I don't know if you can see that there, but according to Mooncalc, yeah, the moon direction was 179 degrees and the altitude was 16 according to theirs. So I was like 70 degrees out. But yeah, I've mentioned this before. If you don't calibrate the app properly, yeah, or you're standing near something metal, yeah, you will actually get a bit of a off reading. All I'm doing now is just making sure that the observations I'm making and match up. And yes, I am using mainstream, but as you can see, it's only for the direction and the actual angle of the moon. What I do then, I just compare it with what NASA's telling us. So NASA are telling us that yes, the moon is at apogee, and as you can see, we're in the exact same phase there. So the moon is at apogee then. So what I did then, I used a measuring tool to actually measure the moon in pixels. So as you can see there, I don't know if you can see that with on your screen, but the moon measured 227.56 pixels. Yeah, so just keep that in mind, because that was the first reading when the moon was at apogee, and apogee is the moon's furthest point. So then on the 27th of October, I waited till the moon was at its closest point at perigee, and I repeated the observations again. Same again, I waited till the moon was at my zenith, which is at 180 degrees. It's just a fraction before there, but it's not too far off. So you can see now, when the moon's closer, it is actually high on the Tropic of Cancer at this point. That does change, and I'll go into that in a little bit. So if I compare that with Mooncalc, there you'll see the reading's 179.77 and an altitude of 53 degrees. So it's pretty close, that, you know what I mean? My observations are pretty close to what mainstream is telling us the direction of the moon. Again, just compare them phases at NASA. As you can see, it's the exact same phase. So just to keep in mind, when we measured the moon first time, it was 227 pixels. So when we measured perigee, guess what? It's 248 pixels. So it's grown significantly. And if you put them side by side, you can just about see with the naked eye that the moon on the right is slightly bigger. So there is actually a point where the moon is closer and does appear bigger, and when it's further away and it does appear smaller. Now, what I did forget to mention is I'm using the exact same focal point on the camera. So I've got the Nikon Coolpix B700, which has got a 60 times zoom. So the maximum focal point on that for optical is 1440 millimeter, equivalent to a 35 millimeter camera. Yeah, so I always make the same observations at the same focal length, which is 1440 millimeter. The P900 shoots at 2000 millimeter, so I'm sure people who've got that, they know it. When you're on the moon setting and you click the 2000 millimeter and it goes to its optical zoom there. So what I've shown here is that there is an anomaly and it can be measured, but like all observations, you know what I mean, I like to repeat it to make sure it's not a one-off, because you never know, do you? So what I did again, I set out in September, this time when the moon was at apogee on the 20th September. Go through the exact same process again, same focal length on the camera. The moon is at my zenith, 180 degrees. Compare that with what mainstream's telling us. You can see again, the moon is at apogee. One thing I did forget to mention, I actually made this observation when I was in Fuerteventura. Yeah, that's not the UK there, by the way. That's actually Fuerteventura. So I took the opportunity to actually shoot the moon at apogee when I was in a different country. You know what I mean? To see if I got some different results, which is always good to do. You know what I mean? To have from different locations. As you can see again, according to NASA's globe model, the moon is at apogee again, so it's at its furthest point. So when I measured the moon again, as you can see, 228 pixels. So it's actually smaller again. So every observation I'm making is actually matching up. You know what I mean? So there is an anomaly, whether we like it or not. Yeah. And then again, my last observation, which was only like 2 weeks back on the 25th of November. Yeah, the moon was at perigee, at its closest point. So I took the opportunity to capture the moon again, just to complete the 4-part observation. And there you can see 180 degrees, my zenith, high in the sky again at 56.7 degrees. So it's quite high in the sky. Again, what I'm doing, I'm checking with MoonCalc to see if my observations are accurate, because it'd be a bit daft if I got a reading of 180 degrees and I looked on MoonCalc and it said it was 270 degrees west, then there would be questions asked. So let's look on NASA's model. As you can see, the moon is at its closest point at perigee now. And if you look at the measurement there, it's now 250 pixels. So there is a significant change in size. So on the left, you've got the moon at apogee, and on the right, you've got the moon at perigee. So there is quite a big difference. And what I've got here, I've just got a little animation just to show you them differences. So there you can see the moon at apogee. There you'll see the change in size at perigee, slightly bigger. Then again at apogee, the one from Fuerteventura. So even when you're actually getting closer to the moon, it's still appearing smaller. So, and there's the last one I recorded in November. And just to keep in mind, all them were shot using the Nikon Coolpix B700 at the exact same focal length, which is 1440 millimeters, which is equivalent in 35 millimeters. What I'm going to do now, this is an example of how I collated all my data. I didn't just take somebody's numbers for it and use them, I actually went online and actually worked out the meridian passing times between the moon occupying one spot and occupying the spot on the following night. That's how I got my time frame, or my marker, to actually measure my observations against what the moon's actually doing. So for an example, on the first night, on the 6th of March, what I did, I went on to the meridian passing on 6th and 7th of March, and I measured that time frame, and I used that to see if it was matching up with my observations. I have actually got a spreadsheet I'm going to get out in a minute, so I'm going to... So my first observation on March the 6th, you'll see the moon took 24 hours and 57 minutes to occupy the same spot on the following night. Then you notice a week later, when the moon speeded up on the equator, look at the meridian passing time there. It took 24 hours and 45 minutes to occupy the same spot. So what I'm shooting in reality is matching up with what's happening in reality. So I can say that my observations are pretty accurate, even though it's quite a crude way of recording the speed of the moon, letting it pass your screen on your camera. It definitely works, and I'll show you with my further observations later on in the presentation. And as you can see again, on March 21st, the moon actually slowed down. That's what got me thinking about the circle model, that if you was on a circle model, wouldn't the moon speed up to cover the more ground? That was my thinking at the time, but I've moved completely away from models now. All I'm going to say is the Earth's flat because there's no measurable curvature over large bodies of water, not because it's a pizza or a Pac-Man or whatever you want it to be. So as you can see, them readings, there was all from my location, Ripley, UK meridian passing for March 2017. When I first posted my original moon race video, someone says, yeah, but when the moon's further away, it will appear to move slower because of parallax, you know. So when a celestial object is further away and it will appear smaller, it will take longer to actually cross your screen. So he says that's what would happen in reality. So what I did, I took readings from the equator. I basically went on to time and date, exact same month, but I took the readings from the equator. And what you find is you get the exact same results. Even from their perspective, if you did the experiment from the equator, you'd get the same results. There you see on March 6th, 7th, the moon took 24 hours, 57 minutes to occupy the same spot. On the 12th, it speeded up, took 24 hours, 46 minutes. Remember, they're ahead of us, so it would have been actual there on their time, because there's quite a lot of time difference between the equator, especially in Pontianak, Indonesia. And then again on March 21st, 24 hours 49 minutes. So that's from two locations, but I went even one step further. Then I took readings from a place in Ushuaia, which is on the southern tip of Argentina, which is on the exact opposite southern latitude to the UK. And guess what? You get the exact same results again. So it doesn't matter where you are on the plane, the moon should always speed up from that perspective. So that's quite interesting in itself, because that surprised me, that I expected some slight variation in numbers, but they're exactly the same. Everywhere you go, that moon will appear to speed up from their perspective. It doesn't matter where you go on the plane, New Zealand, Australia, it will always speed up, and time and date confirms that, which is very interesting. I looked at the daylight hours from Ushuaia, and we get 17 hours daylight on our summer solstice on June the 21st, and Ushuaia on December 21st gets the exact same amount of daylight hours on their summer solstice, but on the opposite latitude. So that's quite interesting as well. This is me hard at work. I just made a little time lapse of me actually collating the data. This is a 2.5 hour time lapse. But this is just to show you that, you know what I mean? I didn't just take somebody else's numbers for granted. I actually worked out the meridian passing data myself. You see how I sit up with my back? Because my back's aching that much. I'm like trying to stretch my back at the same time. Look, that's why I keep sitting up like that. It's quite funny. Well, there I'm gone. And I'm back. So more observations. So we've seen now that when the moon leaves the Tropic of Cancer and heads towards the equator, it speeds up in its cycle. Not only my observations show that, but it's backed up by that meridian passing on time and date, and it clearly shows that when the moon leaves the equator and heads towards the Tropic of Capricorn, it slows down in its cycle. What I just want to show you now is it's not a fluke either. If you look at these readings, every single one in yellow there is when the moon heads from the Tropic of Cancer to the equator. And what you'll notice, it always speeds up at that point. Look, 24 hours, 42 minutes, 24 hours, 42 minutes, 24 hours, 43 minutes, 24 hours, 42 minutes, 24 hours, 43 minutes, 24 hours, 42. At that point, every single time. And what I did, I created a graph. It looks like a heartbeat. And we all know that everything is electrical. If we die, touch wood, what do they use to bring us back to life? Electricity. Everything around us is electric. The sky's electric. Yeah, we generate magnetic fields, and so does the sky. And clearly that the moon is like a pulse. If you put it into a graph, it looks just like a pulse. So it just proves you that the moon, when it does speed up on the equator, it's not just a fluke. It happens regular, and that's over a full year. So more observations. So we've seen, I've just said this, but I'll say it again. We've seen the moon now that it speeds up when it leaves the Tropic of Cancer and heads towards the equator, but then it slows down. But what's the moon doing when it actually leaves the Tropic of Capricorn and heads back north to the Tropic of Cancer? Well, let's find out, because I've captured the moon coming back as well to complete the observations. So this time I waited till the moon was on and around the Tropic of Capricorn, as you can see there from my good friend Jose Silva. His time lapse, the moon's below the celestial equator in what I call the southern circuit. Also, I just want to mention that everything I'm referring to in this presentation is celestial phenomena and not terrestrial. Yeah, there is a difference. Yeah, when I'm talking about poles, I'm not talking about geographical poles on a ball Earth. I'm talking about magnetic poles, like on a magnet. So I just wanted to make that pretty clear. I'm talking about celestial phenomena, which is measured in declination, and not terrestrial, which is measured in degrees. So on the 5th of the 8th, which is the 5th of August, 2017, at exactly 11:40, on these observations, I went a step further. I included the times. Not only did I include the times, I've actually took measurements of the actual radius of the moon. Yeah, this is something I'm always improving my observations. Yeah, so this time I went one step further and actually measured the radius of the moon. And as you can see, on the night of the 5th of August, the moon, which was at its furthest point at apogee, measured 371.59 pixels. That's in actual pixels. You can see the little marker at the top there and the little marker at the bottom there, what I used for a measuring tool. As you can see, it's that same moon phase, and you can see the moon is there at apogee. Interestingly, we've already seen the moon speed up on the equator, haven't we, when it was heading towards apogee, but it shouldn't speed up on the way back. That's it. Just keep an eye on that moon, because that moon's going to be coming back towards perigee, and it should appear to retrograde or slow down in the night sky or the day sky, whenever it's visible. As you can see there, 5th of August 2017, same phase. I also took a diopter reading. What you'll see is the moon's low on the Tropic of Capricorn. As you can see again, I took a moon calc reading. My readings are getting slightly more accurate because I'm taking more time and more care to try and make sure my readings match up with mainstream. So you can see there the moon declination angle, 17.3 degrees, and an azimuth reading, which is 178, which is only like 1 degree off south. And there you'll see my reading is 177 and 18 degrees. And then nearly a week later, when the moon was on and around the equator, remember it's coming from the south to the north now. So this is a time lapse I actually captured myself. Yeah, I used to love doing the moon time lapses. So as you can see on my second observation, on the 11th of August, the actual radius of the moon is increasing. So it's actually getting bigger as it gets closer, which is interesting. So 389 pixels compared to 371. As you can see, took another snapshot from NASA's lunar reconnaissance platform, and there you see the moon now is on or around the equator, exactly where it is from my perspective. So azimuth reading there, 179 degrees, bang on south, and a declination angle of 33 degrees, which is round about the celestial equator. Confirmation, see the nice straight line the moon travels when it's on the celestial equator. As you'll see there, look, their readings 179.6 and 32 degrees declination angle. Mine's 179 and 33. So I'm getting more accurate. In fact, if you look at that moon there, if I drop that down 1 degree, it'd be absolutely smack bang in the center. It's not easy pointing a camera phone at the moon and getting it smack bang in the middle. So my final observation, when the moon was on around the Tropic of Cancer, you'll see again it's on the opposite side of that celestial equator in what I call the northern circuit. Now this is interesting. Interestingly, the moon was like monochrome that night as well, and this was one of them examples on that night when it appeared monochrome. You can see it there. It's got a slight grey color to it. The only editing on this picture I've done is by overlaying that measurement tool. That's the only editing I've done on that. That's basically a straight image from my camera onto the computer, and I just overlaid that to measure it. So again, took a diopter reading, 144 degrees at declination angle 48.1. You can see the moon's getting further and further north, and it's getting higher and higher in the sky. And just a quick reading there, you'll see 144 and a moon altitude or declination angle of 48.6. So again, my moon race for August. As you can see now, when the moon enters frame, it doesn't overexpose because I'm learning new techniques with the camera, and I'm learning new tricks all the time, and new techniques. I learn as I go, basically. This moon race video is a lot better quality than the other one, a lot more stable, and the moon doesn't overexpose and look horrible as it comes into frame. I use what you call the AE lock feature on the camera. It's got it on the P900 as well. When you press record, you just have to press the little wheel to the right, and it locks the exposure and aperture and stops it overexposing. It's good for, especially when if you want to shoot like an occult, when you catch a star going behind the moon, it's brilliant for stuff like that because you can just set it at the right exposure and lock it, and then you can obviously see both the star and the moon in the exact same focus, which would be impossible. the moon on the equator took 5 minutes and 20 seconds to cross my screen. On the Tropic of Capricorn, it took 5 minutes 36. But on the Tropic of Cancer, it seemed to take forever. It took 6 minutes 15 seconds to cross my screen. Look at the time difference there. That's huge. So the results. I need to just go back into my spreadsheet here. What you will notice here, my first observations were made in August, but my third observation was actually made in September 12th. There is a reason for that, and the reason were it was cloudy on the night I should have shot the moon, so I had to wait a full lunar month to get the moon back in the same position so I could shoot it again. It doesn't actually make much difference on the actual readings because I'm still shooting the moon when it's high on the Tropic of Cancer. It's just that it was cloudy and it was actually in daytime when I needed to catch it in August, which was quite disappointing because, you know, when you've waited so long to get the moon in a position and then you go out to shoot the moon and it's cloudy, it's like it's soul destroying. If I'd have had to wait for the sun to get in that position, I'd have had to wait quite a long time to to get in that exact same position. So as you can see on August the 5th, my reading, the moon took 24 hours and 49 minutes for the meridian passing time on that night for the moon to occupy the same spot. Then when the moon was on the equator, the moon took 24 hours, 48 minutes. So it's speeding up when it's heading towards perigee. Remember, it speeded up when it was heading towards apogee. It can't speed up both directions. It's impossible. According to Kepler's law of planetary motion and his equal area and equal time law, the moon should spend the first half of its cycle speeding up with just a change in speed of around about 6%, and the same when it's going back the opposite direction. It should never speed up going to and from apogee. That completely destroys Kepler's law. It shouldn't do that. It's impossible. And you're probably thinking, yeah, but you could just put any of them readings on the screen yourself. You know what I mean? I've had to type them in there. Just give you the confirmation first. So when the moon was on the Tropic of Capricorn, it took 5 minutes and 36 seconds to cross my screen, and the meridian passing on that night was 24 hours and 49 minutes. When the moon was on the equator, it took less time, so it was speeding up, and it took 5 minutes 20 seconds, and the meridian passing on that night was 24 hours 48 minutes. It's matching up exactly what I'm shooting in reality. And you know, the moon took a long time to cross my screen. It took 6 minutes 15 seconds. Well, look at the meridian passing time on that night, 24 hours and 57 minutes. It's matching up exactly what I'm shooting in reality. And just to confirm this, I took a little snapshot from time and date, and if you see on the 5th there, 23:39 till 12:28, yeah, you measure that time and you get 24 hours and 49 minutes. And then on the 11th, 3:40 to 4:28 is exactly 24 hours and 48 minutes. So what I'm shooting in reality is backed up by time and date. But interestingly, the moon shouldn't speed up when it's heading towards perigee. Although it speeds up in the globe model, from a globe Earth perspective, it should appear to slow down. So how can it speed up? Magnetism versus gravity. This is an interesting quote taken from a book called Ether and Gravitation. It's by a guy called William Hooper. He's a globularist, but interestingly, he wrote in his book, if either of these forces is to be done away with, it must be the mysterious, intangible, unphilosophic attraction of gravitation, which must be replaced by the philosophic and known attraction of electricity, which can be traced to a physical medium, the electromagnetic ether. He absolutely got it, absolutely smack bang on when he said that. But then he backpedaled and says, no, it doesn't exist. It's gravity instead. It's mad. It just basically backpedaled at the end of the book and says, nope, the ether doesn't exist. It's all gravity. But we know, everybody who's done their research into flat Earth knows that the only true force in nature is magnetism. And we're just going to see a little demonstration now of magnetism at work. There's no sound on this video, so I'll just let it play, and I'll just watch it with you. As you can see there, the magnetic field creates its own vortex motion, because electromagnetism is the only true measurable force in nature. It's the only force that can be measured. Trains in Japan, they don't run on anti-gravity. They run on magnets. So, my hypothesis. What do I think is going on? These are my own thoughts. Some people probably think I'm absolutely crazy. This is my hypothesis. Now, this image is always blown me away, because the actual bright spot is the moon overexposed, and what it did, it created a lens glare reflection and created an image of the moon. So that light there can create that image of the moon. Now imagine that on an epic scale, with the atmosphere acting like that lens and not the camera itself. And that's when I come to the conclusion that the moon is basically a light in the sky, and it's some kind of projection. I'm not talking holographic images here. I'm talking like a natural projection. The light in the sky and the atmosphere acts as a giant lens, and it can create an image of the moon, which this image proves, because that doesn't look like the moon to me. How can that create that? It's an optical illusion. What we're seeing out in the sky is an optical illusion. The moon looks like it's probably about 10 miles away. It lights up the clouds locally around it. You know what I mean? If you look at the moon in the daytime, it's the actual image of the moon looks a bit fuzzy and not very clear, but at night time it always looks crisp and sharp, the image, you know what I mean? A bit like a rear projection screen telly. When you're watching in the daytime with the curtains open, you've got a rubbish picture, but you close the curtains and turn the light off and you've got a nice crisp picture. Same with the moon. I think David Weiss did some interesting experiments with the eclipse, where he showed a similar kind of projected light, and he basically cut that light out to make the eclipse. Might be worth having a little look at that video, what he made of last year, which was quite interesting, and I actually related to it to my research. And also that Steve Torrance and Mike Kavanagh come to a pretty similar conclusion in their electromagnetic Earth video, when they said that the orb of the sun is probably a type of projected image. I've come to the same conclusion, and I'm going to stick to my guns on that. So, the electromagnetic ether. We know that matter comes in three forms. You've got your solid, you've got your liquid, and you've also got gaseous as well. But there may be a fourth. Yeah, and that fourth element may be the electromagnetic ether, which is a luminiferous substance for the propagation of light. Basically, it carries all the heavenly bodies according to their frequencies, altitudes. And the ether is made up of two great vortices, or magnetic fields. And you've got one in the north. There's a time lapse with the camera pointing at Polaris. And you've got one in the south, which actually the stars rotate in the complete opposite direction. And that's from my good friend Paul Kofo, who took the shot facing south from New Zealand. If you put them side by side, there you'll see in the north, the stars rotate in a counterclockwise or anti-clockwise motion, and in the south, they rotate in a clockwise motion. Some people try and say that's perspective. I said it's two magnetic fields, personally. And just like a magnetic field, you see you'll have your vortex motion going one way. On the opposite pole, you'll have your vortex field going the opposite direction. It always goes in the opposite direction. And as you can see there, the moon, when it gets southern declination, it will basically cross the celestial equator, pick up on the ethereal currents in the opposing vortex, and be circling the opposite direction in the southern vortex. And then it will get northern declination, pick up on the northern currents, and be circling in the opposite direction in what I call the northern circuit. If you take a time lapse from around the equator, now if you move that land away, what you would see two vortices separated by the celestial equator. One goes one direction in the north, and one goes the other direction in the south. This is just to try and give you a visualization of what I believe the moon's doing. So when the moon is in the northern circuit, it will appear to circle, and as it picks up on the ethereal currents in the southern vortex, it will circle in the opposite direction. I know that might sound crazy, but if you go onto moon calc and you go to 70 degrees, what you'll find out is the moon will circumpolar from that observation. It'll be visible for 24 hours. So the moon will spend 2 weeks in the northern circuit in a counterclockwise direction. Then it'll spend the next 2 weeks circling the southern vortex in a clockwise motion. So it's basically going in a figure of 8. And I actually named it the Lunalemma. That's my own word I invented for that. We've heard of the analemma. Well, I actually made one up for the moon, and I call it the Lunalemma. And there you can see a snapshot of the moon over a 27, 28 day period. It clearly makes that figure of 8 pattern. Interestingly, someone said to me, well, if the moon is on the southern circuit from your perspective, how the hell do you see it when you're in the north? But we have this thing called refraction. And what you'll see when a celestial object is perpendicular with the observer, you'll get less refraction. But as the moon, from my perspective, gets southern declination, or from the south gets northern declination, what it will appear to do, it will refract. And as that moon gets further and further away in the south, it will actually project further and further into the north. So it will be visible in the north, and going through quite a few layers of atmosphere, you will get something called refraction. And that's why the image of the moon will project itself into the north from the south. People say, oh, I've seen stars through the moon. They see blue sky through the moon. Why is the moon red? There's a lot of questions. Yeah. So what I've done a little bit of research into this. Yeah. Some people will still say they've seen stars through the moon. Every single person I know, yeah, Ali Madge, Jenna Fredo, Ron Hagberg, myself, we're observing the moon on a regular basis. Yeah, I'm talking, you know what I mean? In 2017, I was out in the garden at least 5 nights a week observing the moon. And I have never, ever, ever seen a star through the moon. I've seen a star go behind the moon. I've actually filmed Aldebaran go behind the moon, and it doesn't come out until it passes the old disk of the moon. So even if it was an half moon, it wouldn't pop out in the Terminator shadow part. It won't pop out until it cleared that. Yeah, the old disk of the moon is there. And I'll show you in a minute, because if you do a long exposure shot of the moon, on a crescent moon, what you'll do, you'll light it up, yeah, and you'll see all the actual moon itself. You know what I mean? I'm sure you've seen like a little bit of a lit side, and then they light the other side up. In fact, I've got a photograph of it coming up in the presentation in a minute, so you'll get to see that. So, hello, Mr. Blue Sky. Yeah, there's a lot of people say they've seen stars through the moon, and they've also they can see blue sky through the moon. Well, yes, you can see blue sky through the moon, which on this image you can clearly see it, but in reality you can't see blue sky from the moon. Yeah, because you need to understand how light works. Now, the light spectrum, you get shortwave light, which is the ultraviolet scale of the light, and you get long wave, which is the infrared scale. Now, what happens on the ultraviolet scale is the light scatters easily, and that's what creates the blue sky. When light scatters, the shortwave light, what it'll do, it'll scatter and it will turn the sky blue. So in reality, for an analogy, if you want to think about the light spectrum, think about the sound spectrum. When I make a high-pitched noise, yeah, what'll happen? Your ears will vibrate quicker, yeah, which creates a high-pitched, which you hear a high-pitched sound. If I make a low rumble, your ears will vibrate slower, and you'll obviously hear a low rumble sound because the eardrums are vibrating slower. Now, there's sounds at either end of the scale. So there's sounds we don't hear, like high frequency sounds, and then there's like sounds at the other end of the scale, which is low frequency sound. Alligators make a certain sound which can't be detected by the ear, and bats make a high frequency pitch noise which can't be detected either. So think of light like the sound spectrum, you know what I mean, where the light waves will scatter easily, and when they scatter they turn blue, yeah, and the ones what will penetrate through thick denser atmosphere is the infrared scale. So that's why on this next image what you'll see is, notice these mountains from a distance, what I filmed in Fuerteventura, they're translucent. But do you really think if an object went behind the mountains you'd see it? The answer is no. Yeah, them mountains are solid, but because the light is scattering due to Rayleigh scattering, it causes an optical illusion, and it looks like the mountains are actually see-through. But in reality, you get closer and closer to the mountains, the solid rock. Now, I'm not saying the moon's solid rock, but you get the same effect with the moon, yeah, where the light gets scattered and you can't see, and you can see blue sky through the moon. My good friend Jenniferado shot this picture of the moon here, and as you can see, it's a half moon. And if you look carefully, if you edit that picture slightly, what you'll see the whole moon. Yeah, the whole moon is actually there. Although it looks like you're looking at a half moon, in reality, the whole disk of the moon is always there. If you get the right exposure, yeah, you will be able to light that other half of the moon up. It's just getting the right exposure, you know what I mean? It's difficult. Like I say, it does look like the moon's not there, but in reality, it's always there. There you go. There's a good example. Yeah. You've got a crescent moon, but what I've done, I've overexposed it and I've lit up the dark side. See, normally you would only see the crescent moon in the sky. But what I did, I actually lit up the dark side by overexposing the moon, or doing a longer exposure of the moon, and it actually lights up the whole moon. So that's just to give you an idea that the whole disk of the moon is always there, and no, you can't see blue sky through the moon. And some will say they've seen stars through the moon. Every person I know has been observing the moon has never seen it. Just going on to the red moon. So one of the questions that I've been asked me, well, why is the moon red? Well, this is simply at the other end of that light spectrum, where you've got the short wave, what scatters. So what happens then is the longer waves of light, which are on the infrared scale, will penetrate the dense atmosphere, because as the moon sets, it will be setting against obviously a denser atmosphere. You know what I mean? The lower we are, the denser the atmosphere, and as you can see, that all that white light has been can't penetrate through that dense atmosphere to the observer, and what we see then is we just see the red come through. So that's why the moon is red. And there is a few questions asked about why does the total lunar eclipse moon turn red? Because in reality, it's being blocked, yeah, by something, or something's, you know what I mean? In the globe model, they're saying it's the Earth what's blocking it, but there is definitely something either going in front of that moon or going behind it. That is without a doubt, because the only reason why that moon would turn red is if something is blocking that light, blocking that white light from coming through. And just a quick look there at the actual the light scale. So you've got your ultraviolet at this end of the scale, and you've got your infrared that scale, and you've got all your colors: red, orange, yellow, green. I've always liked this quote from Tesla: if you want to find the secrets of the universe, then think in terms of energy, frequency, and vibration. I've mentioned the moon cycle before, yeah, because there is quite a lot of cycles, and this is not even half of them. There's a lot more cycles related to the moon, and to try and get your head around them all is very, very mind-boggling. So the anomalistic cycle takes 27.55 days to complete a cycle. The sidereal, yeah, which is the point it takes the moon to pass through all the constellations and get back to the same point again, is 27.3 days. The tropical cycle is a point it takes the moon to get from one point on the celestial equator to pass through to the Tropic of Capricorn, back to the Tropic of Cancer, and get back to that same point on the equator again. That's 27.32 days. Then you've got the draconic cycle. Now, this is also known as a nautical cycle, which is basically related to eclipses. When you get a lunar and solar eclipses, there are points within that cycle, yeah, called nodes, which are actually where the moon will line up to be eclipsed. And basically, the draconic cycle is the point it takes to get from one node and back to that same node again, and that cycle is 27.2 days. And the last one, which is on this one, is a synodic cycle, which is actually the phases. So the time it takes the moon to go from new moon to new moon takes 29.5 days. Now, trying to get your head around just them few cycles, if you're trying to think about the moon, you know what I mean, it's quite mind-boggling. But interestingly, the anomalistic cycle is the perfect clock. Plus, I think I'm going to need my calculator for this. Let me just get my calculator up so I can work it out. The average days per year is 365.24. Yeah. If you times that by 4, which is included the leap year, you get 1,460 days. Yeah. So just keep that number in your mind, 1,460 days. Now, if you take the anomalistic cycle, which is 27.55 days, yeah. Now you get 13 of these in a year, yeah. So 2 years would be 26, 4 would be 52, but you have to count the leap year as well. So you'd have 53. So if you take 27.55 and you times that by 53, you get 1,460 days exactly. You get the exact same days, yeah. So the lunar anomalistic cycle is the perfect clock over 4 years. It fits in to the Gregorian calendar or the solar calendar, what we use today, yeah. But in reality, you could use the anomalistic cycle as the perfect clock, which is quite interesting. And so if you think about the dates of the points of apogee and perigee, they literally fall on the exact same day every 4 years. Yeah. So if it fell on the 20th of, say, on the 25th of November, yeah, in 4 years' time, guess what? The moon will be at perigee on the same day in 4 years' time. And what it does, it changes every 2 years. So every point of every point at perigee, 2 years time, switches around, and that point is then becomes apogee. Yeah, they don't fall exactly on the same day, but they're close. But then you have to take into consideration them days at apogee then fall into that 4-year cycle as well, and it continues. So the best measuring tool for me, like if you wanted a really super accurate calendar, would be by measuring the anomalistic cycle. It is quite a lot to get your head around that, and I hope you come across. I explained it quite clear. So basically, the lunar anomaly fits into the 4-year calendar exactly. Yeah, you got 1,460 days for 4 years, and same with the actual cycle when you times it by the amount. So now all this is leading up to one thing, because on the recent eclipse we had back in July, yeah, something really amazing. Well, I think something really amazing happened. Yeah, because what happened is we didn't only have the lunar eclipse. For a lunar eclipse to make, the draconic cycle has to be aligned. Now we know that a lunar eclipse only takes place on a full moon, so the synodic cycle had to be aligned as well with a full moon. The moon was also at the furthest point on the Tropic of Capricorn, so that tropical cycle aligned with the other cycles as well. Yeah, and not only that, yeah, the moon was at its furthest point in the anomalistic cycle apogee, so every single one of them cycles had to align up. Yeah, and what we got one of the longest eclipses in history. You know what I mean? In our history, I'm sure there'll be a lot longer ones previously and in the future. But one thing to keep in mind, the only time you're ever going to see a full 100% full moon is during a lunar eclipse. Now, what you'll see is the moon is completely 100% full. I'll give you an example. Yeah, this is a 99.9% moon. Now, you can see it's like it's 100% around that side, but as you start getting near the top, you can just start seeing it's not actually quite 100% full. So the only time you can actually observe a perfectly 100% moon is during a lunar eclipse. Now, on the night of that eclipse, something interesting happened, and when I looked at the actual numbers, I couldn't get my head around it, and I'm sure mainstream, I've got an answer for it, but I haven't found that answer yet. And believe me, I've been looking and I've been asking the question. So I call it a lunar standstill. So on the 27th of July, when the eclipse actually started, although the moon wasn't visible from my observation point there, yeah, if you look down here close at this full moon, it's at 100%. So that was at 3:45 in the afternoon. Now, almost 12 hours later, yeah, at 3:01 on the 28th of July, the moon is still at 100% full. Yeah. Now, for the moon, don't forget, moon calc uses a decimal point as well. So, you know what I mean? We're talking decimals here as well. So it's remained full, yeah, at 100.0% for 11 hours, 46 minutes. We have to take into consideration that the moon shifts 13 degrees a day. Now, how can that moon stay full at 100% when it's shifting 13 degrees every single day? It doesn't have days off for lunar eclipses, but I call it a lunar standstill, but that is impossible in the globe model. Yeah, when it's in constant motion, it would be impossible. So people say yes, but it's lined up 180 degrees perfectly. Even so, it's still moving 13 degrees a day, every day. You know what I mean? So to me, that's like a big hole in the heliocentric model. And luckily, on January the 21st, we've got another total lunar eclipse. Same again. All them cycles will all be aligned again, but the only difference this time is instead of the moon being at apogee, the moon's at perigee for this cycle. Yeah, to the exact day it's at perigee. What is the moon? There's been a lot of questions about the moon over the years. When you look at the moon in the sky, it looks like a rock in the sky. It sometimes looks like a sphere. It sometimes looks like a disc. It looks like it emits. It looks like it reflects. Sometimes it looks solid. Sometimes it looks transparent or translucent. It's been there for a millennia, and we still don't understand what the moon actually does or what it is. We know the word month is derived from the word moon, but still, we still don't know what the moon is. And I think the moon could probably sit there for another 1,000 years and we might never, ever, ever know what the moon is. But I know one thing it's not, and it's not that. That's supposed to be the Discover Epic satellite, which is 1 million miles from the globe Earth, if you want to believe that. And as you can see, that's supposed to be the backside of the moon. Rob Simon would probably say it is Photoshop because it has to be. But that is supposed to be a real image of the moon taken from the Discover Epic satellite 1 million miles out. And as I mentioned before, my goal is just to find a little piece of that puzzle. If I can maybe contribute one piece of that puzzle towards finding out where we actually live, I'll be happy, and hopefully I can wake a few people up on the way. But that's my goal, just to find one little piece of that puzzle. That's it. That's my presentation. I hope you enjoyed it.